Okay, we have been talking about this Fermi Dirac integrals. So last time we talked about evaluating these integrals. So we have to keep this in mind that the two integrals of interest. That so our aim is at the back of our mind we have this issue of specific heat. So the two important integrals which I will try to get an expansion and then get an approximate solution to those integrals are namely the number of particles n is given by integral from 0 to infinity d epsilon a of epsilon into probability of epsilon. This is what is your Fermi Dirac function. So, and your internal energy is equal to integral 0 to infinity d epsilon a of epsilon into epsilon into p of epsilon. So these are the two integrals that we would like to get. And of course here your a of epsilon is the density of states, okay, which is given by v divided by 4 pi square into twice m by h bar square to the power 3 by 2. In the last class we had done we have used this density of states to get these things in terms of the Fermi Dirac functions, if you can recall. And your P of epsilon is given by 1 by Z inverse e to the power beta epsilon plus 1, or I can write this as 1 by e to the power beta epsilon minus mu plus 1. So this is your Fermi Dirac occupation, the average occupancy or the probability of occupation of this energy level E. Okay, so we have to evaluate these integrals. Now it turns out that evaluating these integrals is quite difficult. So we have to only evaluate approximately. Okay, so it can be evaluated approximately. Okay, so let us try to understand how to evaluate these integrals. Now this is important because once you get your u, okay, so once you get this, then your specific heat is simply derivative of u with respect to temperature. So we are interested in specific heat of electrons in metals or electronic specific heat of metals, which we have argued in a heuristic manner that it should go like T. Okay, so this we have to get it. We have to get this result. That is the aim of this calculation. Okay, so now we have to understand the nature of this function. And as I told you that the important thing that we have to understand is that so let us try to get some idea about this function, which we have seen in the previous case. So suppose if I plot, let's say this is your epsilon and this is your P of epsilon. Okay, So this is the probability. Then, as I told you that this one is a step function. This one is a step function, and this is your Fermi energy at t equal to 0. Okay, and as I showed you in the last class, for any higher temperature than the non-zero temperature, you can see that this one is more or less same at higher temperature and lower, at higher energies and lower energies, and around this particular Fermi energy, there is a deviation. So this is basically for some temperature T, such that T divided by Tf is much less than 1. As we discussed in the last class, that you have for room temperature, for example, for any typical metal, this is of the order of 10 to the minus 3 to 10 to the minus 2. Because Fermi temperature for the metals is of the order of anywhere between 10,000 Kelvin to 1 lakh Kelvin, 10,000 Kelvin to 100,000 Kelvin. That is what is the typical Fermi temperature for metal. Now, suppose if I ask suppose if I am interested in plotting, let's say I'm interested in plotting dP by d. Okay, so how does dP by d looks like? So let's say that we want to plot dP by d. Suppose if you want to plot this, so since here it is a straight line parallel to x-axis, the slope is always 0 here, and slope is always 0 here. So there is going to be a change in slope, and this change in slope is very steep. Okay, so you can see that if I plot this one, dP by dE will be 0 here, and it is also 0 here, and there is going in. Remember, the slope is decreasing; it's a negative slope. So you are going to have some kind of a dip like this. Okay. So this is the graph of dP by d. Okay, and if I want to invert this one, I want a peak. I just plot minus dP by d. So note that our understanding of the behavior of this function minus dP by d epsilon is a sharply peaked function at at mu, basically a chemical potential, because remember this epsilon f is mu at t equal to 0. So it is actually a sharply peaked function at mu. So in other words, if I draw minus dP over d epsilon versus epsilon, and if you have mu somewhere here, then this is going to be a sharply peaked function around this epsilon equal to mu. Okay, so this is something, if you understand the behavior of this function, then let us go back to this. Let's go back to this expression. So consider your n. Okay, so I will write n. So n is equal to. So I have V divided by 4 pi square into twice m by h bar square to the power 3 by 2. Okay, integral 0 to infinity epsilon to the power half. Okay, that is my density of states into 1 divided by e to the power beta epsilon minus mu plus 1 e epsilon. Okay, so what I will do is I will simply call this one as v by 4 pi square. Now this epsilon is getting integrated out. So what will this be? This will be a function of mu. So I will write this as v by 4 pi square into twice m by h bar square to the power 3 by 2 into, let me just call this integral alone as I of mu. So that I will only concentrate on evaluating this I of mu. Okay, so now I want to find I of mu. First, let us do an integration by parts. Because what we have is P of epsilon, but we know dP by d epsilon is a sharply peaked function. So if we integrate this by parts and get dP by d epsilon, then we can concentrate only around mu. We don't have to worry about other distant energies far away from mu. Okay, so that is what we want to do. So in that case, what I will do is, so you know this I of mu is equal to minus mu plus 1, okay, and dV as epsilon to the power half into d epsilon. So this is like my u dV, and then I will have my V is equal to 2 by 3 epsilon to the power 3 by 2. Okay, and what about my du? Du is equal to minus 1 by e to the power beta epsilon minus mu plus 1 the whole square into e to the power beta epsilon minus mu into beta. Correct? So this is what is my minus integral 0 to infinity. So there is a 2 by 3 that I can put outside. Epsilon to the power 3 by 2 into beta e to the power beta epsilon minus mu divided by e to the power beta epsilon minus mu plus 1 the whole square. I think there is a minus sign sitting here, so this becomes a plus sign. Okay. Now I could have simply done it like this. Okay, so there is another way to simply look at it is that let's keep. So in other words, I could have written this n as or okay, let us write I mu. I can write this I mu as integral 0 to infinity epsilon to the power half into p of epsilon d epsilon. Okay, so I can simply leave it as p of epsilon d epsilon. And then if you do integration by parts, so there I take my u to be p of epsilon and dv to be epsilon to the half d epsilon. So now du is dp by d epsilon into epsilon, and your v is 2 by 3 epsilon to the 3 by 2. So this is, in that case, what our I of mu can be written as. Okay, there is nothing wrong in what we have written. I'm just trying to show that in a simple way, 3 by 2 into p of epsilon, starting from 0, evaluated at 0 and epsilon, minus integral 0 to epsilon 2 by 3 epsilon to the power 3 by 2 into dp d epsilon into d epsilon. So this is same as this, of course. I have expressions here and I don't have expressions here. But now look at this one. At the lower limit, because of this epsilon power 3 by 2, this will become 0. And at higher limit, upper limit, this will become 0 because your P of epsilon, whatever is the temperature, as epsilon goes to 0, your P of epsilon is always 0. Okay, as epsilon goes to infinity, your P of epsilon is always 0. And hence, this term is equal to 0. Okay, the first term is 0. Okay, so first term is 0 since P of epsilon goes to 0 as epsilon goes to infinity, and epsilon to the power 3 by 2 goes to 0 as epsilon goes to 0. Okay, so the first term does not contribute anything. So my I of mu is equal to 2 by 3 into integral 0 to infinity epsilon to the power 3 by 2 into minus dp by d epsilon into d epsilon. Now remember, this minus dp by d epsilon is what we have plotted here. Okay, so this is the plot of minus dp by d epsilon. It is a sharply peaked function. So I have written here that note that minus dp by d epsilon is a sharply peaked function at mu, and in our integral now we have that minus dp by d epsilon here. That means basically this integral is area under the curve. So this area under the curve will be you will be interested only, you will be it is sufficient if you just consider a small region around mu to evaluate this integral, because minus dp by d epsilon is 0 very far away from mu on either side. and hence it is sufficient to consider the integral around mu because of the sharply decaying nature of this minus dp by d epsilon on either side of the chemical potential. So this is essentially the crux of the matter. So we have this.
So sir, we can take this as Dirac delta function.
No, if it is a Dirac delta function, then the answer is very simple. But it is not Dirac delta function, but it is somewhat sharply peaked function. So we can actually concentrate around mu. Okay, so that is what will help us to make an expansion in terms of any given function around epsilon is equal to mu. Okay, it is not Dirac delta function.
Okay, sir.
Okay, so Dirac delta function is kind of the zeroth order approximation, but in general, it is there is some kind of a distance around mu over which there is an appreciable change in this. But Dirac delta function is one extreme consideration of this. That is in this class of behavior, but it is not as sharp as Dirac delta function as such.
So for t equal to 0, can we take that Dirac delta function?
Yeah. So for t equal to 0, you can take this to be Dirac delta function of epsilon at epsilon f. Okay, so that is what we have done. Okay, so I think what you have observed is correct. So at t equal to 0 Kelvin, because that is a step function and derivative of step function is a Dirac delta function. At t equal to 0 Kelvin, your minus dp over d epsilon can be written as delta of epsilon minus mu, but mu at t equal to 0 is what is called the EF. Okay, so this is correct observation. Okay, but not at non-zero temperatures. Non-zero temperatures, there will be some finite width for this. Okay, so we have this expression here, and this expression is so whatever this expression that I have. So this expression is what is given by minus dp over d epsilon. Okay. Okay. So now what we will do is okay. Now what we will do is, since okay, so let me put it this way. Since the integrand is 0 for except for some epsilon around mu due to minus dp by d epsilon, of course, we can expand epsilon to the power 3 by 2. We can expand epsilon to the 3 by 2 in Taylor series. In Taylor series around mu. So that means we are going to say that our epsilon to the power 3 by 2, I can write it as mu to the power 3 by 2 plus epsilon minus mu into d epsilon to the power 3 by 2 by d epsilon evaluated at epsilon is equal to mu plus epsilon minus mu the whole square by factorial 2 into d2 epsilon to the power 3 by 2 by d epsilon evaluated at epsilon is equal to mu and so on. So I can expand this in Taylor series around mu. Okay, so what is this term? This is 3 by 2 epsilon to the power half. And this is 3 by 2 into 1 by 2 into epsilon to the power minus half. So I have at least these three terms. Let me write down mu to the power 3 by 2 plus epsilon minus mu into epsilon to the power half, and of course there is a 3 by 2. Sorry, I have to evaluate this at mu, so that is mu to the power half plus epsilon minus mu the whole square by 2 into 3 by 2 into half into mu to the power minus half, and so on. So once we have this expression, we can go back to this integral. So substituting this in the integral, okay, so we have our I of mu is equal to 2 by 3. Okay, so let me go back and then substitute in this expression itself. There is so there is a beta that I will pull out, and integral 0 to infinity. So I have this expression, that is mu to the power 3 by 2 plus epsilon minus mu into 3 by 2 into mu to the power half plus epsilon minus mu the whole square divided by 2 into 3 by 4 into mu to the power minus half, and of course I have all our additional terms. This into, now I have to write down the minus dp by dt expression. Beta I have already written outside. So I have e to the power beta epsilon minus mu divided by e to the power beta epsilon minus mu plus 1 the whole square. And what is this integral over d epsilon? Okay. So this is, so now you have to integrate this term by term. Okay. So let us try to integrate this in the following fashion. So first what we will do is let's make a change of variable. Okay, so define some variable x which is equal to beta times epsilon minus mu, so that your dx is equal to beta times d epsilon, or your d epsilon can be written as dx by beta, and this implies your epsilon minus mu is basically x by beta, or kbt into x. Okay, so if I use this, remember there is a beta here, so we get this I of mu to be 2 by 3 into beta integral 0 to infinity integral 0 to infinity mu to the power 3 by 2. And what is epsilon minus mu? Epsilon minus mu is kbtx. kbtx into 3 by 2 into mu to the power half plus kbtx the square divided by 3, and then you have 8 into mu to the power minus half, plus there are other terms which I have not cared to write now. So this is e to the power x divided by e to the power x plus 1 the whole square into dx divided by beta. So this beta that is sitting outside and this beta can be cancelled. Okay. Now we have, so let me write down this I of mu as, let's say, I1 of mu plus I2 of mu. Okay, I do not know, we call it as I0, I1 plus I2 of, plus of course you have so many other integrals which I did not write here. So what is I0 of mu? Or you can say 2 by 3, I can just take it here, 2 by 3 into this, because this 2 by 3 is sitting outside. So what is I0 of mu? I0 of mu is mu to the power 3 by 2 into, of course, I think I have to be careful. So the limits of integration are not 0 to infinity here, because, so remember, if epsilon is equal to 0, okay, so x is equal to beta mu or minus beta mu. Correct? If epsilon equal to 0, and epsilon infinity implies x also goes to infinity. There is no problem. So the lower limit on this integration is minus beta mu. So minus beta mu to infinity. That is what this is. So minus beta mu to infinity e to the x by e to the x plus 1 the whole square and dx. That is this term. That is the first term here and then this term. That is our I0 of mu. What is I1 of mu? I1 of mu is, so there is a 3 by 2 kbt mu to the power half into integral minus beta mu to infinity. You have e to the x, because there is a ktx here, remember, ktx. So x e to the x divided by e to the x plus 1 the whole square dx. That is our I1 of mu. and I2 of mu, I2 of mu is equal to 3 by 8 and kBt the whole square into mu to the power minus half into integral minus beta mu to infinity x square into e to the x divided by e to the x plus 1 the whole square. So I have written only 3 terms, and these 3 terms are like this. Okay. So now we have to evaluate these 2 terms, these 3 terms. And remember, so far we have not made any approximation. We are only trying to just use the fact that this particular function, Fermi Dirac function, whose derivative is behaving this way, and we are making use of that behavior to expand the integrand in terms of around epsilon equal to mu, and we have kept all the infinite terms. So there is no approximation done as such. Okay. Now we are going to make one approximation. So the approximation that we will make here is to solve these integrals. Okay, to solve these integrals, note that when when t by tf is much less than 1. Okay, so this is generally called degenerate limit. The limit t equal to 0 is called the degenerate Fermi gas. So your temperature is not very high, it is much smaller than your Fermi temperature. Then you can say that your beta mu, which is basically equal to mu by kBt, is somewhat like your epsilon f by kBt. Okay, and this is much larger than 1. Much larger than 1. Okay, and since this is much larger than 1, okay, so that is beta mu is much larger than 1, and the integrands in the above integrals are sharply decaying functions. Around basically x equal to 0, because if x equal to 0, then our epsilon is equal to, that means epsilon is equal to mu, because you remember epsilon minus mu, beta into epsilon minus mu is your x, okay, around x equal to 0. So there is no loss of generality if we extend the lower limit of these integrals to minus infinity. There is no loss of generality because anyway the integrand is 0, slightly away from x equal to 0. So already we know that this beta mu is a very large number. So let's say it is minus some large number. But even at that number it is 0. So going to minus infinity, anyway this function is 0. So it's not adding to the area anyway. So there is no loss of generality in extending this limit to 0. So this is an approximation, of course. It's not. This is called degenerate limit approximation. So this is the first approximation that we are making. So with this approximation, we can see that so this particular. So first, let us look at what is. We'll try to evaluate each one of these integrals. So let's first write what is I0 of mu. I0 of mu is equal to mu to the power 3 by 2. Okay. And you have minus infinity to plus infinity e to the x by e to the x plus 1 the whole square dx. Okay. Now remember this this situation that I have. So what is this function? Okay, this function, if you recall, this function is exactly this function, right? So it is minus dp by d epsilon. Okay. So if you are trying to say that I have so note that if I have a function f of x which is equal to minus 1 by e to the x plus 1, then what will be df of x by dx? Df of x by dx is minus e to the x divided by e to the x plus 1 the whole square. Correct? Yes, sir. So this is e to the x by e to the x plus. Or if I have a minus sign here, then this will be plus. So this is like this integral is like mu to the power 3 by 2 into minus 1 by e to the x plus 1. Okay, evaluated from minus infinity to infinity. Correct. So because this is a derivative of this function. So now that is equal to mu to the power 3 by 2. And if I put plus infinity, e to the infinity is infinity. So 1 by infinity is 0. Okay, so let me put this minus sign outside. So first I get 0 minus, if I put this minus infinity, okay, so this becomes 0, e to the minus infinity is 0, then I will have 1. Correct? So this integral is, there is a minus sign outside, so simply mu to the power 3 by 2. Or this integral is 1, that's what it means. Okay, so this is mu to the power 3 by 2. So we have evaluated the so I0 of mu is simply mu to the power 3 by 2. Okay, now let's go to second, that is I1 of mu. I1 of mu is like this. So 3 by 2 kBt mu to the half. So now let's consider I1 of mu, which is equal to 3 by 2 kBt into mu to the power half, integral minus infinity to infinity, x into e to the x divided by e to the x plus 1 the whole square dx. Now I am going to use a trick here. So I will write this integral as 3 by 2 into kBt mu to the half. I'm going to write this integral in the following fashion. E to the minus infinity plus infinity, x e to the x divided by the denominator. I'm going to write it as e to the x plus 1 into e to the x plus 1. This is basically whole square. Now I will take this e to the x in the numerator to denominator, and then I can write this as 3 by 2 kBt into mu to the power half, integral minus infinity to infinity. So there is a dx sitting here. So x dx divided by e to the minus x plus 1 into e to the x plus 1. Why? Because when I take this to the denominator, it will multiply with one of these things. That will become e to the minus x into e to the x, that is 1, and e to the minus x. That is what this is. Now notice that, so note that the integrand is an odd function of x. Odd function of x. Because if you take x going to minus x, this term will become this term and this term will become this term. So denominator will not change, but because x is x going to minus x, this will change sign. So this is an odd function. Now minus infinity to infinity, integral of an odd function is 0. Okay, and therefore your I1 of mu is 0. Okay, so this is a simple trick which will, by looking at the expression, initially it doesn't appear like this an odd function, but by doing a little bit of analysis, you can recognize that this is an odd function. Now let's come to the second I2 of mu. Okay, so I2 of mu is 3 by 8. Okay, so now I2 of mu is 3 by 8 kBt the square into mu to the power minus half, integral minus infinity to infinity, x square e to the x divided by e to the x plus 1 the whole square. Okay, now this is something which we have to evaluate, because this is an even function. in the same logic as we have seen earlier, this is an even function. Okay, so this needs to be evaluated. Okay. Now, in order to evaluate this one, you have to so let's say that okay, maybe we can consider a slightly general integral itself, like okay. So let me put it this way. So first, I can uh, write this integral minus infinity to infinity x square e to the x divided by e to the x plus 1 whole square dx can be written as 2 times integral 0 to infinity x square e to the x by e to the x plus 1 the whole square dx. Okay, so that is, we have to now just evaluate this one because this is an even function. I can always write it like this. Now we can try to do an integration by parts. Okay, so now consider, so I will write this as my, so now consider integral 0 to infinity x square e to the x divided by e to the x plus 1 the whole square dx, and do an integration by parts. Okay. So what kind of integration by parts I do? I consider my u to be equal to x square, okay, and dv as e to the x divided by e to the x plus 1 the whole square into dx. Then du is 2x dx, and v is minus 1 by e to the x plus 1. That is integral Hello? Yeah, I actually lost internet connection, so I do not know when. So did you listen to up to what stage? I1 equal to 0?
Sir, we were doing I2.
I2, okay. So
Yeah.
up to
Bypass.
bypass. Okay. So that's all. I think there was nothing much done. So this is so there is a 2 here and there is a 2 here. So it becomes 3 by 2 kBt the square, and you have mu to the power minus half. So mu to the power minus half, and integral 0 to infinity. I have x dx divided by e to the x plus 1. Okay, so this is something we have to evaluate. This integral has to be evaluated. So let us try to evaluate the slightly general integral. Okay, so let me just, okay. So we can consider consider an integral which is integral 0 to infinity from x to the power p minus 1 dx divided by e to the power x plus 1. Because even if you keep higher order terms, this kind of terms are the ones which you are going to get. So let us try to evaluate this. So this is equal to, so we can evaluate this integral 0 to infinity x to the p minus 1, and I can write this as e to the minus x into 1 plus e to the minus x to the minus 1 dx. So what I did was I pulled out e to the x and take it to the numerator. Then I write 1 plus e to the minus x to the power minus 1. And I expand this binomially. So that will be equal to integral 0 to infinity x to the p minus 1 e to the minus x into 1 minus e to the minus x plus e to the minus 2x minus e to the minus 3x plus and so on into dx.
Sir,
Yeah.
sir, in the last integral, did you took the 2 by 3 factor?
2 by 3. Why?
In I mu, there is a 2 by 3.
That I did not write I mu. No, I only wrote I2 mu.
Okay, sir.
I mu we have not come yet. We will come to that. I am just evaluating. I didn't complete evaluating I2 mu itself.
Okay, sir. Okay, sir.
So little bit of patience. So this is equal to integral 0 to infinity. I can write this as x to the power p minus 1, and I will write this as sum over, let's say sum r is equal to 1 to infinity minus 1 to the power r minus 1 into e to the minus rx. Okay, so when you put r equal to 1, that is plus, r equal to 2, it is minus, and so on. So this I can write it as, I swap the summation r is equal to 1 to infinity minus 1 to the power r minus 1 into integral 0 to infinity x to the power p minus 1 into e to the minus rx. Because there is a dx. Okay, so now this I can write it in the following fashion. So now you set rx is equal to some t, then dx is equal to dt by r, and x to the power p minus 1 is equal to t to the power p minus 1 divided by r to the power p minus 1. So integral limits don't change. So this is equal to sum over r equal to 1 to infinity and minus 1 to the power r minus 1 divided by r to the power p, and integral 0 to infinity e to the power p minus 1 into e to the minus t dt. And this by definition is a gamma of p. So I have r equal to 1 to infinity minus 1 to the power r minus 1 into gamma of p divided by r to the power. Okay, so this is the evaluation of this integral. Now you can see that this means, okay, so this means your integral 0 to infinity x to the power p minus 1 dx divided by e to the x plus 1 is equal to, so let's say you have some gamma of p here, and then this is an infinite series. What is that infinite series? If r is equal to 1, that is 1, then minus 1 by 2 to the p plus 1 by 3 to the p minus 1 by 4 to the p, and so on. Okay, so now let me write this in the following fashion. So let me say that this is equal to gamma of p. So first let me write down that this has 1 plus 1 by 3 to the p plus 1 by 5 to the p plus 1 by 7 to the p, because these are all odd things with plus sign. Okay, so this is one infinite series. Then I have minus 1 by 2 to the p plus 1 by 4 to the p plus 1 by 6 to the p, and so on. Okay. Now you can see that suppose if this is 4 to the p can be written as 2 to the p into 2 to the p, 2 to the p into 3 to the p, like that. So this is, I can write this as gamma of p into, so what I can do is, okay, so anyway, let me write this first. 1 by 1 power 3 to the p plus 1 by 5 to the p plus etc. minus 1 by 2 to the p. If I pull that out, then I have 1 by 1 plus 1 by 2 to the p plus 1 by 3 to the p, etc. Now, this one, what is there in this bracket is basically a Riemann zeta function. Okay, so this is equal to gamma of p into 1 plus 1 by 3 to the p plus 1 by 5 to the p, etc. minus 1 by 2 to the p into a Riemann zeta function of p. Now I want to put everything in terms of this Riemann zeta functions. So what I will do is add and subtract. Add and subtract this infinite series, that is 1 by 2 to the p plus 1 by 4 to the p plus 1 by 6 to the p, etc. to the above series. Now since you are adding and subtracting, you are not doing anything. So now what happens if you add them, then this bracket, okay, so if you add and subtract, then what happens? This integral 0 to infinity x to the p minus 1 dx divided by e to the x plus 1 will become gamma of p into, if you add, this one will become zeta of p, the first one, when you add it. Then when you subtract, that will become this 1 by 2p into zeta of p. Okay, the subtracted one is also minus 1 by 2 to the p into zeta of p, and then you already have minus 1 by 2 to the p into zeta. So that is equal to, you have this integral is gamma of p into zeta of p into 1 minus 1 by 2 to the p minus 1, because this is 2 by 2 to the p. So 1 minus 1 by 2 to the p minus 1. So this is what is the general result. Okay. Now we don't want general result, even though we have done it, but we want to find out. So our requirement. So our requirement for I2 of mu is p is equal to 2. Correct. That is our requirement. So we want this integral, that is integral 0 to infinity x dx divided by e to the x plus 1. We want this. That is essentially gamma of 2 into zeta of 2 into 1 minus 1 by 2 to the power 2 minus 1. So that is equal to gamma of 2 into zeta of 2 divided by. Now gamma of 2 is 1 factorial, that is 1, and zeta of 2, I do not know if you have ever evaluated that in your Fourier series class, and that is given by pi square by 6. Okay, zeta of 2 is pi square by 6. Okay, so if you have not done this, that is your zeta of 2 is equal to 1 plus 1 by 2 square plus 1 by 3 square, etc., etc., etc. This is something which can be shown as pi square by 6. Okay. There are many ways of showing this, but usually people do it using Fourier series of some function. So our integral is now given by pi square by 12. Okay. Now let's retrace our path back. So where is our integral? So this is our integral. I have pi square by 12. Okay, so this integral. Okay, so let's try to. So this integral is evaluated, and this integral is pi square by 12. Okay, and now let's go back to I mu. Yeah, here. So I0 is I0 mu is just mu to the power 3 by 2. I1 is 0. So I2 is what we have obtained here, 3 by 2 kBt square into mu to the minus half. Okay, so let us write that. So I have my I mu is equal to 2 by 3 into, this is the 2 by 3 that Abhijit was reminding, mu to the power 3 by 2 plus 3 pi square by 24. There is a 3 by 2, and then I have kBt the square into mu to the power minus half. Okay, I think that's all that I have. Yeah, mu to the minus half, 3 by 2 pi square by 12. So 3 pi square by 12 into 2 is 24. So that's what I have written here. So this is my I mu. Okay, what is that I have to do with this I mu? I have to go back and then put it in the integral for n. Okay, what is this I mu? I substituted this I mu here. Okay, so I called this I mu as this integral. Okay, so that means I have to now substitute this in the equation for n. Okay, so now let me write down n is equal to v by 4 pi square into twice m by h bar square to the power 3 by 2 into, we have 2 by 3 into mu to the power 3 by 2 plus 3 pi square by 24 kBt the whole square into mu to the power minus half. Actually, I am saying that I am only evaluating up to this. There are higher order terms, but somehow let me say that okay, this is something that is enough. Okay, so this is an expression for the, this is an expression for n in terms of mu. Now suppose if I pull this mu out, okay, so I can write this as, so let me write down this n by v as let us keep it like that. So v by 4 pi square into twice m by h bar square to the power 3 by 2 into 2 by 3 into mu to the power 3 by 2 1 plus 3 pi square by 24 into kBt square by mu square. Okay. Now I want you to notice that if you want to write down, so let's look at what would have been our zero temperature result. Okay, so let's look at zero temperature result. So at 0 Kelvin, what would be our n? n is equal to v by 4 pi square twice m by h bar square to the power 3 by 2 into integral 0 to epsilon f epsilon of d epsilon. Is that correct? That will be our n, right, in at zero temperature result. So that is equal to v divided by 4 pi square into twice m by h bar square to the power 3 by 2 into epsilon f to the power 3 by 2 into 2 by 3. Correct. So this is our n, and the number of electrons are not going to change. Our number of fermions are not going to change. Okay. So maybe what we can do is we can try to. So what we will do is, so we write. So let us write this v divided by 4 pi square into twice m by h bar square to the power 3 by 2 into 2 by 3 as n divided by epsilon f to the power 3 by 2. Okay, let's write like this in this expression. Okay, so if I do that, then I will have, so this is what I am trying to, so then I have n mu to the power 3 by 2 divided by epsilon f to the power 3 by 2 into 1 plus 3 pi square by 24 into kBt the whole square divided by mu square. So now you can see that this is what is your n. Okay, so this n will cancel. So you will have something like mu divided by epsilon f. Okay, mu divided by epsilon f. I can write this as 1 plus 3 pi square by 24 into kBt the square divided by mu square to the power of minus -2 by 3, because this is going to be 1 by, and 3 by t will become -2 by 3. Now you can write this as mu by epsilon f is equal to, now this is like a correction term. At temperature T equal to 0, mu is exactly equal to epsilon f. That means the first term is there. Now the second term, you can say this is a correction, and this is valid because this kBt is much smaller than your epsilon f. So I can write this correction term mu as epsilon f, and then write this as 2 by 3 into 3 pi square by 24 into kBt the square by epsilon f the square. Okay, so if I write like this, then I will get an expression for the temperature dependence of this mu, which is equal to epsilon f into 1 minus pi square by 12 into kBt the whole square by epsilon f square. So this is temperature dependence of the chemical potential. Okay, so this is the temperature dependence of chemical potential. Now you can see that chemical potential. So note here that mu decreases as T increases. The highest value of mu is only epsilon f at T equal to 0, because this is 1 minus this one. So as temperature increases, the chemical potential decreases. And of course, classically, the chemical potential will be negative. So it will start from some positive value, it will cross 0, and then it will become large negative value. That is why, if you remember, we have the variation of chemical potential is from minus infinity to plus infinity. Okay, so that is so this is very important to understand that this is how we get temperature dependence of various physical quantities. Okay, so this is not enough, because we have to now find out. So do another integral. Okay, so now doing other integral is not very difficult, because we have understood how to do. So our next task is so our task now is to get an expression for u as a function of time. Okay, for which we have to evaluate u is equal to integral 0 to infinity d epsilon a of epsilon into p of epsilon. Now everything else is same, except that in the above integral, okay, so in the integral above, we have, so you write u is equal to v by 4 pi square twice m by h bar square to the power 3 by 2 into integral 0 to infinity. There is a root epsilon here and epsilon here. So I have epsilon power 3 by 2 into p of epsilon. Now when you do integration by parts, okay, so when you do integration by parts, so same thing is valid. So when you do integration by parts, so on integration by parts, you get u is equal to, the first term anyway will cancel, so I'm not going to write that, twice m by h bar square to the power 3 by 2 into, I have 2 by 5 into integral 0 to infinity epsilon to the power 5 by 2 into minus dp by d epsilon. This is what I get. So what do I do in my expansion? I now expand epsilon to the power 5 by 2 in terms of so in terms of So now I can say that equivalent to my I of mu earlier is equal to 2 by 5 into integral 0 to infinity. Okay, so I have mu to the power 5 by 2 plus 5 by 2 into mu to the power 3 by 2 into epsilon minus mu, of course, plus 5 by 2 into 3 by 2, that is 15 by 4 into mu to the power half into epsilon minus mu the whole square divided by 2, and so on, into this expression d minus dp by dx into dx. So you get same kind of thing. I1 will be mu to the 5 by 2. That is I0 will be mu to the power 5 by 2. I1 will be 0 and I2 is same as whatever we have done. So I can write this I of mu to be 2 by 5 into mu to the power 5 by 2 plus 15 by 4 mu to the power half into kbt the square divided by 2 into whatever is the expression that I have here. Okay, so this 3 by 2, yeah, so I think I should have that 4 sitting there. Wherever that I have 3 by 8, you know. So this 3 by 8, this will be equivalent to our 15 by 8 here. And so I will have a 4 into pi square by 12. So that is my result. Now remember this. Why this 4? This 4 is because there are some two factors that I have used here. Okay, so let me. Okay, here I have 3 by 8. Now there is a factor 2 here, and then there is a factor 2 here when I converted minus infinity plus infinity into this one. So these two will give me on 4. So I'm just not doing it, but I recommend you do this carefully. So that is equal to 2 by 5 into mu to the power 5 by 2 plus 15 by 2 pi square, 15 pi square by 2 into mu to the power half, mu to the power half into kbt square. Okay, so now I can go back and then write this here. So this integral, so u is equal to v by 4 pi square and twice m by h bar square to the power 3 by 2 into 2 by 5. So let me put this. Let me pull out mu to the power 3 by 2 here. Then I will have mu plus 15 by 2 pi square into kbt the whole square by mu square. Okay, this is what I have. So now I go back and then.
Sir,
Yes.
sir, will that be 15 over 2 or 15 over 24?
Okay.
Sir, in the last line, You have written 15/2 pi square kbt square over mu square, right?
Correct.
Sir, I think this will be 15/24 because the I of mu epsilon.
Correct. You're right. So this is 24. Yeah, thank you. So now let's go back to this thing. I have written this this one. Now, of course, here I don't have 2/3. I have 2/5. So let me say up to this, I will write this as 3/2 into n. This one. So what I will do is I will write up to this as 3/2 into n divided by epsilon f to the power 3/2. Okay, so this is equal to that. Then you have u is equal to 3/2, so that is 3/5 into n mu to the power, or mu by epsilon f to the power 3/2 into mu plus 15/24 pi square into kbt whole square by mu square. Okay. Oh, sorry. This is n by, that's fine. So, three by five n okay. So suppose if you are looking at so examine T equal to 0 Kelvin. At T equal to 0 Kelvin, your mu is equal to epsilon f. Okay. So that means you have mu equal to epsilon f. This becomes 1, and this is epsilon f. So your u is equal to 3/5 into n epsilon f. This can be neglected because kbt t is equal to 0, so this will be neglected. So we have this result that we had seen, that the u by n is 3/5 into epsilon f. So this is our zero temperature result, and that is borne out in this particular case. So now I have to get this expression. Okay, so I have to now say that so I will write this u as 3/5 n into mu to the power 5/2 by epsilon f to the power 3/2 plus 3/5 n mu to the power 3/2 by epsilon f to the power 3/2. Yeah, that is there. Then 15/24 into pi square divided by kbt the whole square by mu square. Now you can see that this first term is like so if we set epsilon, if you set mu is equal to epsilon f and t is equal to 0, then we get we get u is equal to 3 by 5 n epsilon f, of course, as expected. Okay. So now what I will do is I will try to pull out this factor, and I will call that as some u naught, okay, into 1 plus. So I have pulled out 3 by 5, and 3 by 5 is there, n is there, and mu power 5 by 2, epsilon this is there, and mu power 5 by 2. That means I have to multiply and divide by mu. So that will give me 1 plus 15 by 24 pi square into kbt the square divided by mu cube. Okay, but now I am interested in getting an expression for this one, that is equal to u naught into 1 plus 15 by 24 into pi square kbt the square, and we already know what was mu. Mu was 1 minus sorry, that is okay. So let me put it this way: epsilon f the whole cube. Remember what was mu? Mu is equal to epsilon f into 1 minus this this quantity, right? So that is equal to 1 minus. So essentially, this is 1 minus pi square by 12 into kt by epsilon f the square, and this whole thing raised to the power 3. If you have to write it like this, but then this is uh, something that you can write. So you can write this as u naught into 1 plus 15 by 24 pi square into kbt whole square divided by epsilon f cube into 1 minus pi square by 12 kbt whole square divided by epsilon f square to the power minus 3. Okay, so it is like this term can be this term maybe I'm not correct in writing like this. I hope I didn't make any mistake. So mu to the power half. Yeah. Oh, okay. I think there is. So if I pull out, so this is not correct. So if I pull out mu to the power 3 by 2, this will be simply by mu only, right? Remember, I am trying to take, so I multiply, or this term, I multiply and divide by mu. Then this becomes mu to the 3 by 2. So this is not mu square. This is simply mu. Correct. So I think this is just mu. So I think we have to change this everywhere. This is just mu. So as a result, what happens when you write like this? This becomes mu square. Okay. So I think now we have, so this will be epsilon f whole square, and this is epsilon f square, and 1 minus 2. Okay, so I think we don't have to worry about the second term because we just keep the first term, in which case I will get u0 into 1 plus 15 by 24. So that is basically 5 pi square by 8, and kb e the square divided by epsilon f square. So this will be our u of t. And as I told you that we had almost got this expression earlier, but only this factor I call that time as a, and that is given by this 5 pi square by 8. Okay, I hope I am right, but please check in some book if this factor is correct. If it is not correct, then I think we have made some mistake in calculation. It looks like it is correct. So this is our u of t, and then just we are one click away from this CV. CV is essentially 5 pi square by 4 into, okay, there is a u not sitting there, 5 pi square by 4 into kb square into t by epsilon f square. So you can see that this is the expression, and which is very small. Why it is not observed to have contributed for some temperatures? Because the temperature of the specific heat due to phonon contribution varies quite rapidly, whereas because this epsilon f square sitting in the denominator, this is a small addition and hence it is not possible to observe. But when you go to low temperature, then the lattice contribution and electron contribution are more or less comparable, and therefore you will see that this contribution is observed in the low temperatures. And that is where I said that the specific heat will go like gamma T plus alpha T cube, and gamma T is the contribution that is coming from the electrons. And of course, this U0 is 3 by 5 n into epsilon. Okay, so this is the story of Fermi Dirac integrals and Sommerfeld's expansion. So Sommerfeld expansion is a technique which is used to find the properties of ideal Fermi gas, and that is what we try to discuss today. Okay, I'll stop here, and if you have questions, we can discuss. Any questions?
Excuse me, sir.
Yeah.
Sir, I have doubt in previous class.
Oh, okay.
I mean, sir, I found it difficult to show that W remains unchanged when we interchange a number of quantas with number of particles.
Previous class means one class before, or
No, I mean, some 1, 2,
no,
3.
the older class.
Solar cluster. Number of ways of distributing quantas to particles.
Okay.
I found it difficult to show that when we interchange, W remains unchanged.
Okay. So this is you're talking about that Bose
Yes, sir.
distribution.
Yes, sir.
So essentially, we have this W. So this W is given as n plus m minus 1 factorial divided by n factorial into m minus 1 factorial, right?
Yes, sir.
This is what we write it as n plus m minus 1 into c m minus 1 or whatever. But this
Yes,
is
sir.
same as n plus m minus 1 en, right? The coefficient is same, right? Because this is a binomial coefficient.
Okay, which one? I'm not C and n plus n minus 1.
See, what I'm trying to say is that
Yes, sir. Now n can be replaced by m minus 1.
yeah. So
And but we said
not
n can be replaced by m.
no. See, what I'm saying is that when you have so many quantas and so many partitions, okay, like these partitions. So if you have n particles,
n minus 1 partitions.
n minus 1 partitions are there.
That,
So when I'm saying you can replace, we have to replace like that only. So and you have m quanta. Okay. So it is only these partitions and quanta that are replaced.
okay, sir, okay. That I understood, sir. But we said particles can be interchanged. That part I felt it.
Yeah. Particles means only in terms of okay. It is not exactly particles. It is only partitions.
That okay. That and that part.
That is what is correct.
Okay.
Because the n minus 1 is what can be interchanged.
Fine, sir. NCR equals NC n minus R.
Exactly.
Okay. Okay, sir.
Okay. Any other question?
Excuse me, sir.
Yes.
Sir, how to experimentally determine that at low temperature the CV is actually going like T, because the T cube factor will also be there by phonon contribution. So
Correct. Yeah. So one I think I mentioned this last time. One way to do this is that your CV will have something like this: gamma t plus alpha t cube, and this is because of the lattice. And you cannot separate it. When you do an experiment, you get the contribution for the both. So what one does is they will plot this CV over T versus T square. That means you measure CV as a function of temperature. Okay. So like in laboratory notebooks, you write temperature, CV, and then you take T square and CV by T, and then plot these two things. Then you will get a straight line. So you are getting a straight line in this graph it means that the CV is like this. And you can get gamma and alpha from here. Okay, so that is the way to extract information about the linear dependence of specific heat. I think this is your question, right?
yes, sir. So even if I divide CB by T, so it will be basically gamma plus alpha T square. So with
Correct.
T square it will be linear. So
Correct.
okay, sir. Yeah. I got it now.
Yeah. Okay, so if no questions, then Shruti, we can close. Okay.